All right, we're taking a look at worksheet number 25. The questions we need to go over are 3, 5, 7, 10, and 12. Question number 3 on our worksheet says, the original activity of polonium-210 is 100 becquerel. What's the activity after 2 years have elapsed? I believe, yes. I think I probably know what the mistake that, or the problem that people had with question number 3 is. You need the half-life of polonium-210, right, in order to do this question. If you look back to question number 1, they tell you in question number 1, or I tell you, that the half-life of polonium-210 is 138 days. So 138 days is the half-life. 2 years have elapsed, which is, what's that going to be, 730 days? We want to be in the same units, whether we use days or years. I think days is a little bit easier here. The original activity, n sub 0, is going to be 100. So in this case, we're looking for 100 becquerel, BQ. Doesn't matter what our units are. Remember, we said if you see one of these half-life problems and you see units that you don't even recognize, it's probably going to be either n or n0. It's going to indicate an amount. A becquerel, if you're not familiar with that, is a decay per second. It's the rate of decay. But that's an amount of decay. 100 decays per second is my original amount. My final amount is what I'm looking for here. So let's say n is equal to n sub 0, 1/2 to the little n. Little n we got to find by saying t over t 1/2, the one that doesn't appear on our data sheet. 730 days divided by 138 days. That gives us 5.2899 half-lives, which we're going to turn around and plug into here, 100 times 1/2 to the 5.2899. That gives us 2.56 becquerel. So what was the issue with that? Whoever asked me, was it the half-life? Okay. Sometimes when you see a worksheet, we do have to go back to a previous question for data. If that happens on a diploma exam, and it can, right? It can happen on a diploma exam where we have to go back to a previous question. But if it does, it'll all be grouped together. The questions will all be grouped together where it says, use the following information to answer the next 4 questions or whatever. You won't have to, on question number 36 on your diploma exam, go back to question number 4 on your diploma exam to get a half-life or something like that, just to the information that goes before it. Next question was number 5. On worksheet number 25, we need the half-life of carbon-14. That's probably the issue again with this one. The half-life of carbon-14 from a couple of questions that we've already done is 5,730 years. We know that n here, the number of half-lives that have gone by, that have elapsed, is 3. We want to know what the original, we know the activity at a certain point is 20.0 becquerel, 20 decays per second. We want to find out what the original activity was. So we're going to do n is equal to n sub 0, 1/2 to the little n. We're going to rearrange that to solve for n0. It's going to be equal to n over 1/2 to the little n. N is 20 becquerel divided by 1/2 to the 3. So as it turns out, we didn't actually need the half-life here. You didn't need to go back to the information you had learned over the last couple of days. We're given the number of half-lives. That's good enough. When you solve that, it worked out to be 160 becquerel. You know that you should get a number that's bigger than what we have in the end here, because 3 half-lives have gone by. Okay, if we now have 20, then we must have started with something bigger than 20. 160 seems reasonable. Next question, number 7. One of these ratio questions, right? We see that from time to time, and they seem to always throw people off. What do we do whenever we're asked to find a ratio of anything? Something to something. Doesn't matter what the something is. One word, starts with a D. Divide. You want to find a ratio? We always go back to that example of my age to your age, right? Okay. The ratio of my age to your age is about 2.5. How do we get that? We divide my age, 40, by your age, 16, and we get 2.5, or at least approximately 40. Divided by 16 is 2.5. So we divide the two numbers. Easy enough. Okay, here we want to find the ratio of the current activity to the original activity. So we're going to divide n by n sub 0. That's easy enough. If we know the value of n and n0, then let's just divide them. N over n0 is equal to whatever. But if we don't, then let's say a half to the 11,460. That's going to be 2 half-lives, considering that the half-life of carbon-14 is 5,730 years. A half to the 2 is 0.25. So we get n over n sub 0 is equal to 0.25. The ratio is 0.25 to 1. Good? The easiest way to do a ratio problem is if you have the value of this and the value of this, and you just divide them. But if you don't, then let's get an expression that equals n over n0, which, of course, is going to be 1 half to the little n. We're just rearranging the equation that we have. True?
So I know that like 1/4 is that ratio.
Yep.
Is that ratio wrong?
Like 1 to 4? No, that's right. 1 to 4 would be the same as 0.25 to 1. No. In fact, it's probably a better way to say it, because 0.25 to 1 kind of doesn't sound great. It's right. It doesn't sound great. 1 to 4 sounds better. Now, on your diploma exam, they give you 4 answers for this, right? Be prepared for 0.25 to 1. Be prepared for 1 to 4. Okay, they're both correct. I mean, I don't think they'd ever do something like this, but be prepared for 16 to 64, because it's still the same thing, right? We just got to recognize that the second one's got to be 4 times the first one. Yep. Yep. No, the current activity is going to be the smaller amount. So current to original. My current activity is 0.25, 25% of what my original activity was. So it's going to be 2.25 to 1 or 1 to 4. Okay, if it said what's the ratio of the original activity to the current activity, well, my original activity is always going to be more. So you could say that would be 1 to 0.25 or 4 to 1. Okay, does that make sense? Always divide the one that it says, find the ratio of x activity to y activity. It's x over y. If it's, I don't think so. It's a possibility, I suppose, but I don't think that they would do that. Okay, that's kind of a trick almost. They like to give you hard questions. They do. But they generally don't try to trick you into putting a wrong answer. Okay, number 10. 10 says, how many half-lives would it take for a radioactive sample to decay to 25% of its original activity? Well, let's say N0 is equal to 100%. We're going to find out how many half-lives it takes to decay to 25%. Now let's make N0 100%. We're looking, N would be 25%. And we're looking for a little n here. How many people did this question using the divide by 2 method? Okay, how many people did it using logarithms? Seems like most people like logarithms. We'll do it both ways here. After 0 half-lives, I've got 100%. After 1 half-life, I've got 50%. After 2 half-lives, I've got 25%. Little n is going to be 2. Done. Or you could do it using logarithms. You could say n is equal to log n over n0 over log of 0.5 or log of a half. Either way you look at it, it's going to be equal to 2. And finally, question number 12 is the graphing question. We had a graph that looked something like this. As we always do when we've got a radioactive decay curve, it's always going to look like this. The number is on the left-hand side here. On the y-axis, the time is on the x-axis. That y-axis could be anything that is n. It could be grams, it could be percent, it could be a number, anything that's n. Okay? Big N, that is. Starts at 60 here. We want to find the half-life. Remember, it's always going to be up and over or over and down. We want to find the half-life. Let's go down to 30. Why did I pick 30? Why did I pick that number 30 to go over and down? that just a random pick? Yeah, it's half of what I started with. I started with 60. I've got 30 now, and it looks like that appears to be about 1 when I go over and down, about 1 day. How much of element X remains after 2 days? Well, let's go over to 2 days here on our x-axis. Let's go up and over. When I do that, it appears to be about 15. So 15 would remain after 2 days. How much remains after 3 half-lives? Well, the half-life here we said was 1 day. So how much would remain after 3 half-lives? How much remains after 3 days? Let's go up and over. And it looks to be about 8 remaining after 3 days. And finally, how long would it take for element X to decay to from its original amount to 10 nuclei remaining? Let's go to 10 nuclei remaining here. Let's go over and down. And it appears to be about 2.5 days. You see, in all 4 questions, I either went up and over or over and down. And of course, the graph that I have drawn on the board isn't quite to scale. So you look at this 8, 10, 15. It doesn't look like it works out. But if you have a graph that's drawn to scale, like we do on our sheet, then it does work out more or less to those numbers. I will tell you that on an exam or in a test, you're likely to have not a better graph per se, but better grid lines. Better grid lines on the graph, so it'll be easier to tell, whether it's 8 or 9 or 7.5 or whatever. Yep. No. In fact, we don't want you to do it with the equation. Okay. Well, yeah, I'll tell you what. Actually, it would be okay in this case to do it with the equation, because if you take the half-life from the graph, okay, then that would be okay. You should get the same answer, but at least pretty close to the same answer. But if what we don't want to do is take data points and use any mathematics, use any equations with it. Okay, you never want to take data points. If you've got something from the graph, a number from the graph like a slope or something, and you want to use that in an equation, then you go ahead. But you don't want to take a single data point and ever do that. Okay. All right. We're good with that worksheet? Good. As I was checking it over with you guys, it looked like it went pretty well for everybody. There's a few people that had issues with 1 or 2 questions, but in the end, looks like it's going okay. We'll write our quiz here now. We'll see how that goes, and then we'll move on from there. Spent a few minutes reviewing fission and fusion. Can you tell me, please, there's 2 equations up on the board right now that describe the transmutation of elements here. Can you tell me which one is fission? And tell me which one is fusion. Let's say number 1. Let's say number 2. Can you tell me which one's fission, number 1 or 2? Joel? Number 2 is fission. Good. We did fission first, so you kind of expect fission to be listed first on the board here. It's not. Fission is number 2, and fusion is number 1. We can tell that because you can see, independent of the neutrons here, forget about the neutrons where you're trying to identify what's what. We can see that in equation 2, one big element splits apart into 2 lighter nuclei. One big one splits apart into 2 lighter ones, 2 smaller ones. In the first one, you can see that 2 smaller ones come together to form 1 bigger one. That's all we got to do. That's all we got to look at. Okay, if 2 big ones, 2 small ones, I should say, combine to form 1 big one, then that's fusion. If 1 big one splits apart into 2 smaller ones, then that's going to be nuclear fission. Even if it's an equation that you've never seen before, doesn't matter. Okay, fission is 1 splits into 2. Fusion is 2 comes together to form 1. Now, in fission, we had a neutron here that we had to add to the left-hand side, or to the reactant side, to the parent side. Anybody tell me why we had that neutron on that left-hand side? What was the purpose of that? Go ahead. Okay, so that 3 neutrons on the right side could go back to the uranium. Okay, ultimately, that's how we get the 3 neutrons on the right-hand side, yes. But a little bit more directly, This thing is radioactive, but we want to cause it to decay into krypton and barium, and we want to do it a little bit quicker than it naturally would decay into an alpha particle and whatever. So we fire a neutron at it to make it briefly uranium-236, which makes it unstable and breaks apart into this krypton and barium and these 3 neutrons. That was my next question, though. What's the benefit of these 3 neutrons that come from this nuclear reaction, this fission reaction? Yeah, these 3 neutrons, if the whole setup is proper, these 3 neutrons can go back and react with 3 more uranium-235 nuclei, which is going to produce 9 neutrons, 9 more reactions, 27 more reactions, 81, and so on and so on and so on. What do we call that? When the products of one reaction cause more reactions. We call it a chain reaction, right? This is our fusion one right up here. You can see the 2 hydrogen are coming together, 2 heavy hydrogen, right, an extra neutron in there, are coming together to form helium-3 and an extra neutron and a bunch of energy in there as well. Can anybody explain to me what the difficulty in making these 2 hydrogen nuclei fuse together is? Why are they so difficult? Why is it so difficult to make them fuse together? Why can't we just do it here? Get some hydrogen and, push them together and fuse them together and make a nuclear reactor? What's the issue with that? Yeah. They repel each other. And they repel each other according to Coulomb's law, which means the closer they get to each other, the smaller R gets. What happens to the force of repulsion? It gets bigger, right? So you have to have a really, really big energy or a really, really big force in order to overcome that repulsive electrostatic force that acts between these hydrogen nuclei. Okay, and that energy that you get, that you pump into it to overcome that repulsive electrostatic force usually comes from heat. Okay, it usually comes from thermal energy. Not necessarily, but usually it's going to be some kind of thermal energy or heat energy. All right, how do we get a chain reaction and a fusion reaction? In the fission, we know that the neutrons go on to form 3 more reactions. What is it that keeps the fusion reaction going, the chain reaction sustained? It isn't the neutron, is it? Yeah, it's the energy. Now, not all of that energy goes back to causing more reaction. Otherwise, it would be basically an energy neutral reaction, right? You have to get more out of it than you have to pump back into it, okay, to make it an exothermic reaction, to make it a useful reaction. Where's the most common example of nuclear fusion that we see? Where does it happen all the time? And we see it, well, I was going to say every day, but we don't necessarily see it every day in Alberta. The sun, yeah. What's mass defect? We can find it in 2 ways. If you can give me one of them, then that's good. Jordan? Good. The difference in mass between the nucleus and the nucleons. What's a nucleon? Good. The protons and the neutrons. So when you add up the mass of all the protons and all the neutrons, you get a number that's different than the mass of the nucleus itself, which I know sounds really weird, but it is what it is. Can you tell me whether the nucleus is heavier or the nucleus is lighter than the nucleons? In other words, when we add up the mass of all the nucleons, the protons and neutrons, do we get a number that's bigger than the nucleus itself, or do we get a number that's smaller than the nucleus itself? Yep. Good. The nucleons weigh more than the nucleus itself. So the nucleus will be lighter than the sum of all the nucleons. That's one way that we define the mass defect. What's the other way? And probably, to be honest, the more practical way for us. Yep. Yeah, products and reactants, parent and daughter nuclei, okay, whatever you want to call them, it doesn't really matter. The difference in mass between the left side and the right side. Which is going to weigh more? If there's a difference in mass, then clearly one of them is going to weigh more. Which one's going to weigh more, the left side or the right side? The reactants or the products, the parent or the daughter? In a nuclear reaction, we always lose mass. Mass disappears. So the parent is going to be heavier. The nucleons, okay, are going to be heavier than the nucleus. The parent, or the left side, is going to be heavier than the daughter, or the right-hand side. That mass defect, that missing mass, doesn't just get destroyed. Okay, we have, in chemistry class, we have the law of conservation of mass. We say that mass can't be created or destroyed. Well, it can't be, but it does disappear, okay, when we have a mass defect. But it's not destroyed. Where does it go? Where does that missing mass go? Where do we see that missing mass? True? It goes to energy. And we call that energy the binding energy. Binding energy can be defined in a couple of ways as well. One is the energy that's required to put a nucleus together. But the other way that we can define it, and the way that's way more practical for us and the problems that we're going to do, is the energy that's released as a nucleus breaks apart. Okay, and when we have a nuclear reaction, it comes as a result of a nucleus breaking apart, maybe reforming, okay, but in the end, a nucleus breaking apart. So that's what we got to look at here. The binding energy is the energy that's released when a nucleus breaks apart. In other words, it's the energy that's released in a nuclear reaction. Now, how do we find that binding energy? Einstein's really famous equation that lots of people don't understand. You guys all do, but lots of other people out there don't understand it. E, energy, M, mass, C, the speed of light. This M in particular this time is the mass defect. So the amount of mass that's lost in the nuclear reaction multiplied by C squared. The amount of mass that's lost in kilograms multiplied by C squared gives us the energy that's released in joules. Now, sometimes we've got to convert that to electron volts, but that's something that we did months ago. Good? All right, we had two other bits of homework as well here. Two other questions on page 794. These both use a couple of things that we learned yesterday, one being the equation E is equal to mc squared, and the other one being this whole idea of an atomic mass unit. We defined that yesterday as the mass of 1/12 of a carbon-12 atom, which made the mass 1.66 times 10 to the minus 27 kilograms. The conversion factor for that, by the way, is on the left-hand side of your data sheet. So if you don't remember that number, that's okay. Just check your data sheet. If you need it, it's there. Let's take a look at both of these questions here fairly quickly, okay? One says, find the energy equivalent in electron volts for 0.221 atomic mass units. First things first, we don't like electron volts, and we don't like atomic mass units. We're going to convert both of those. Okay, we're going to convert atomic mass units to kilograms. That's going to give us joules, and then we're going to have to convert to electron volts. So in the end, two conversions that take place here. Let's do the atomic mass unit conversion first. We're going to say one atomic mass unit is 1.66 times 10 to the minus 27 kilograms equals 0.221 atomic mass units over x kilograms. Does anybody have the value for x there? So, times 10 to the minus 28. Thank you. So now we've got it in kilograms. That's good, because that's where we always want it, in kilograms. Now we're going to say the energy equivalent is equal to mc squared. That's 3.6686 times 10 to the minus 28 times 3 times 10 to the 8 bracket squared. When we do that, what do we get? Not the answer that's on our answer sheet here. I'm going to guess it's going to be somewhere around 3.3 times 10 to the minus 17. 11? Oh, yeah, it's mega electron volts, isn't it? So what is it we equal? 3.3 times 10 to the minus 11 joules, which we're going to turn around and convert to electron volts now, using that old method that we learned a couple months ago. Solve for x, and I think we're going to get 2.06 times 10 to the 8. Is that right? 2.06 times 10 to the 8, which is 206 mega electron volts. I think we'll skip question 2. Okay, question 2 is pretty much the same as question 1, except instead of solving for the energy equivalent, you're solving for the mass equivalent. You still got to convert mega electron volts to joules, and then you're going to solve for the mass in kilograms, and then convert kilograms to atomic mass units. So it's kind of working backwards from question number 1. If you have trouble with that, just let me know, and I can help you with it, okay? Well, here's another question. You're going to love this one. It's not as bad as it might seem, actually, on the surface. Calculate the energy released by the fission reaction. Uranium-235 plus a neutron goes to barium, krypton, and 3 neutrons. How do you find the energy that's released? Well, let me ask you one question, a quick question here first. Where does the energy come from? The energy that's released comes as a result of what? Neutrons? Not exactly. In a nuclear reaction, what happens to release energy? We just reviewed this just a minute ago. Sorry? It's nuclear decay. Yeah, sure. Energy can't be created from nothing. There was no energy. Now there is. Where did it come from? Good. It came from mass being converted to energy. There is a mass defect here, a missing mass. Remember we said just a minute ago, the second way that we define mass defect was a difference in mass between the reactants and the products, the left side and the right side. The left side always weighs more than the right side. Let's get that mass defect. Let's find out how much mass was lost. Then let's convert that mass fairly easily to energy by using the equation E equals mc squared. We need to get the mass of this left side. We need to get the mass of the right side here first. We're going to get the mass of both of those sides, the left and right-hand side, by this table that we saw yesterday, right here. Now, I've cheated a little bit and written those numbers down on a piece of paper so that I wouldn't have to keep flipping back to that page. Okay, in the end, it's not hard to do. It's easy enough to get those numbers off of that table. Uranium-235, if you looked on that table, you would see that uranium-235 has a mass of 235.043930 atomic mass units. Remember, I'm not just making that up, or I'm just not coming with that out of my head. I don't have it memorized. Okay, this is the number that appears on the table. I just don't want to go back to the table for each of these numbers. A neutron is 1.008665 atomic mass units. Barium is 140.914412 atomic mass units. Krypton is 91.926156 atomic mass units. And a neutron is 1.008, but we've got 3 of them. So it's 3 times 1.008665, which is, I didn't write that down. So it's 3 times 1.008665, whatever that equals. Now, we said we don't like to work in atomic mass units. This would be the exception. In the end, when we do a calculation, we have to be in kilograms. But I don't want to convert all of these to kilograms right now. Let's get the mass defect in atomic mass units, and then let's just do one conversion from atomic mass units to kilograms. So let's add these guys up. On the left-hand side, the reactant side, the parent side, we have a total mass of 236.052595 atomic mass units. On the right-hand side, if we add all those up, we end up with a total mass of 235.866563 atomic mass units. This isn't so hard yet, is it? You just got to get those masses from the table, add them up, get the total mass on the left side, get the total mass on the right side. What do you think we're going to do next? What comes next now that we have the mass of the reactant and the mass of the products? Subtract them. Good. Let's subtract them. The mass defect equals 236.052595 minus 235.866563 atomic mass units. By the way, if you ever get a number on the right side that's bigger than the left side, you're wrong. Just like when we did elastic and inelastic collisions. If the kinetic energy final is bigger than the kinetic energy initial, you were wrong. Try it again. Do the subtraction here. This one works out to be 0.186032 atomic mass units. Now, at this point, we would like to just say E equals mc squared and get the energy. But we need to put that mass in kilograms. So let's do the conversion. 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. 0.016032 atomic mass units is equal to x kilograms. X equals 3.081312 times 10 to the minus 28 kilograms. So now we've got a mass defect in kilograms. To finish it off, what are we going to do? To get the energy that's released in the fission reaction, what are we going to do? It's a pretty simple step at this point. Question? Is it a question with the rearranging of that? So 1 over 1.66 is 0.01 over x. The x goes up by multiplying. The 1.66 goes up by multiplying. And in effect, you end up multiplying that number with that number. Yep. Sorry, not 0.016. I don't know where I got that from. It should be 0.186032. The number that we have on the bottom there is still correct, though. What's next? Come on, this is a simple step. We've gone through all the hard stuff now. Joel, what's next? Yeah, and what are we going to do to solve for energy? Not atomic mass. They didn't. Okay, well, we're going to convert it to kilograms. E is equal to mc squared, right? E is equal to mc squared. 3.088 times 10 to the minus 28 times 3 times 10 to the 8 squared gives me an energy of 2.78 times 10 to the minus 11 joules. Now, we could, if we wanted to, turn around and convert that to electron volts or mega electron volts. It all depends upon the question, what they ask me for, right? Joules, electron volts, mega electron volts, or whatever. Is that a really hard question? I don't think it's that bad. I don't think it's that bad. Yeah, I'm going to leave you with a couple of these to work on for homework tonight. That will be your only homework. But because it's 11:25 right now, I want to real quickly go to our next topic, okay? And finish that next small topic up here. Okay, the questions that I want you to work on tonight, page 819, questions 1 to 3. Page 819, number 1 to 3. Some of you are going to be familiar with what we're going to talk about today already. You're going to have learned it a little bit in chemistry class. We're going to talk about the Rutherford gold foil experiment, or sometimes it's called the Rutherford alpha scattering experiment. You remember where we are right now. Okay, Dalton came up with a model of the atom that said the atom is just basically a solid sphere. It's like a billiard ball. Okay, they're all different, but there's nothing inside it. We can't break it down any further. Thomson came along with his cathode ray tube, discovered the electron and said the atom consists of a sea of positive charge with a little electron floating around, or a bunch of little electrons floating around inside it. Big step forward because it acknowledged the existence of subatomic particles, but still the structure of it was all wrong. Rutherford comes along with a couple of assistants, Geiger and Marsden. Geiger, same guy who was the Geiger counter, and performed an experiment that took the model of the atom a huge step forward. Geiger and his assistants had basically a little box. Not a little box of alpha particles, but a little box of radioactive material that produced alpha particles, these helium nuclei. Over here, they have this thin layer of gold foil. It's like tin foil, except even thinner and made out of gold. Like gold leaf. You ever have gold leaf? See gold leaf that sometimes you use in baking cookies or something? It's really, really thin, like minuscule thin gold foil. What these guys did is allowed these alpha particles one by one to leave this box and hit this gold foil. And they observed what happened to them. Now, they observed what happened to them not directly because they couldn't see these alpha particles with their eyes. Of course they couldn't, right? But they could see what happened to them based on where they hit this screen. We call it a scintillation screen. It glows when it's struck by these alpha particles. When these alpha particles were released one by one, these guys, Rutherford and his assistants, made 3 observations. The first observation, most of the alpha particles went straight through. The vast majority of them just kept going straight like this. But they also observed that a few of them, or some of the alpha particles, were deflected. So instead of some of them going straight through, some of them were deflected like this. And they could tell they were deflected because of where they hit the screen. Most of them went straight through, some of them were deflected. A few of them, very, very few, but still a measurable number of them, bounced back. So some of them went back like this. A few of them. What do Rutherford and his assistants conclude from this? Let's use a little analogy for a second and see if you can draw the same conclusion that they did. You got the football field outside. There's 110 yards in a football field. Okay? There's little markers every yard, right? There's lines every 5 yards, right? Every 5 or every 10 yards? Every 5? Okay, so lines every 5 yards. Let's say that we've got a person standing in each of those yard lines that's marked. So we've got, what, 22 people standing right across from one end of the football field to the other end of the football field. Those 22 people are blindfolded. One by one, I say, okay, you, run straight across. Most of those people that run straight across are going to be able to run straight across the football field. Most of them make it to the other side of the football field without any problem. The vast majority of those people just run straight across. But a few of those people that happen to be kind of fairly close together are deflected. So most of them are going across like this. But a few of them, the guy right here, changes his path. This guy changes his path more. This guy changes his path this way. This guy changes his path this way. And then these guys go straight through again. A few of the people, like 1 or 2 of the people that are running across the football field, bounce back this way. What does that tell you about the football field? You're all blindfolded, right? All 22 of you are blindfolded running across the football field. What does it tell you about the football field if most of you run straight across without any interference whatsoever? A few of you kind of get deflected, and then one or two of you bounce straight back.
Just a reminder that grade 11 band meeting in the band.
Probably tells you that there's something there. Tells you that most of the football field, or most of the atom, is empty space. Otherwise, these alpha particles wouldn't go straight through. Most of the football field is empty space. Otherwise, most of you wouldn't run straight across undeflected. But there is something there. There's got to be something there. There's something that's small, and it's going to be positive in the case of the nucleus. What's going to push these positive alpha particles away? Okay, what's going to push these positive alpha particles away right here? Something that's positive. Something that can repel it. There's got to be a small positive nucleus in the middle. It's got to be small because most of the alpha particles went straight through. It's got to be positive because it repelled the alpha particles. Some of them went straight back. What does that tell you about the middle there? Well, it tells you that if you ran at top speed across the football field and you bounced back, then you must have hit something that was heavy, right? Something that was dense. A big football player, a dense football player. I mean heavy football player. That's what I mean by that, right? The nucleus has got to be heavy. The nucleus has got to be dense. So look at where we are right now. The atom did consist, according to Thomson, of C, a positive charge with a bunch of little electrons floating around inside it. Now we've got a small, dense, positively charged nucleus, and the electrons, he said, orbit around it. That's not quite our current model of the atom, but it's a lot closer to what we had than what we had yesterday. Good? All right, so just those 3 questions, practice questions for homework tonight, and we'll pick it up here tomorrow.